Outer space holds a weapon 100 million times more powerful than an atomic bomb. One strike, and it could black out a continent. From the space age to the Stone Age, in a flash. The weapon isn't man-made. It's our sun.
It's always a question of when the next one will happen. It's not a question of will they suddenly go away.
We've been hit before. We're in its sights again. Quebec, March 13th, 1989. The city is in the grip of winter. Temperatures are below freezing. Suddenly at 2:44 a.m., a 100-ton transformer on the Montreal power grid overloads. Blackout. The city is plunged into darkness. 6 million people left powerless. Astronomer Sten Odenwald explains how the night unfolds.
All the lights went out, quite literally. It only took about 90 seconds for fully operational to complete blackout conditions.
At dawn, the thermometer reads just 8 degrees, and the power's still out. Life or death work runs on emergency generators. The blackout lasts 12 hours. But the disaster could have been much worse. If not for a few transformers in the US, millions of Americans might have lost power too.
With only a couple of more components damaged, the entire East Coast would probably have gone down as well.
But what caused the transformers to overload so violently? Why did Quebec plunge into darkness? This wasn't a terrorist attack or human error. The culprit wasn't of the Earth. It was the result of a gigantic explosion 93 million miles away on the sun. Three days before the power network collapses, astronomers at the Space Weather Prediction Center in Colorado monitor an active region on the sun, when suddenly, a giant explosion bursts from its surface. A white flash thousands of miles across and millions of degrees hot. 93 million miles later, a huge wave of radiation slams into Earth's atmosphere. Colored lights dance across the night sky from Alaska to Mexico. Quebec is hit by an invisible but immense natural phenomenon. A solar storm. An explosion of the sun so awesome, and a wave of energy so huge, it's almost impossible to measure. Space weather scientist Joe Kunches is blown away by the scale of these storms.
Billions or trillions of tons of matter is thrown off the sun at 1 million or so miles per hour. And I think it bodes towards the difference between terrestrial weather scales, where you might have wind speeds in the extreme of hundreds of miles an hour in a very strong hurricane or a tornado, to looking out at the solar wind, and the solar wind typically is 1 million miles per hour.
The solar storm that hit Quebec is the worst in living memory. But worse may strike the Earth in the future. And next time, we might not be so lucky. The sun is capable of producing storms that could black out whole continents. North America would be crippled.
Losing the electric power grid, even temporarily over an entire continent, is a major disruption to the way we operate in the 21st century.
Our lives are more complex and technologically advanced than ever before. But the freedom technology brings us could also be our downfall. Anything relying on the power grid when a solar storm strikes is vulnerable. But what causes a solar storm? How do they wreak so much havoc here on Earth? And is there any way to protect ourselves from future attacks? Scientists need to unravel the mysteries surrounding the sun and reveal the anatomy of a solar storm. The investigation begins 93 million miles away. The sun is a 900,000-mile-wide ball of gas, mainly hydrogen. It's so vast, you could fit over 1 million Earths inside it, with room to spare. All the sun's energy is generated deep within its heart, at the core. Temperatures here reach 27 million degrees, thousands of times hotter than Earth's most extreme forest fires. Every second, millions of tons of hydrogen are converted into helium. This nuclear fusion produces over 5 million tons of energy. The sun radiates more energy in 1 second than the world has used since time began. The byproduct of all this energy is vast amounts of magnetism. Huge magnetic fields loop across the surface. They bubble up from the core and punch hundreds of thousands of miles into the solar atmosphere before plunging back down again. These arcs are so vast, the Earth could fly through one, with 100,000 miles to spare on each side. On planets like the Earth, every part makes a full revolution around its axis each day. But the sun is a dynamic ball of gas. Its equator rotates in 25 days, but the poles take 35 days. The magnetic loops stretch and distort as it turns. Along each loop flow billions of tons of superheated plasma, electrically charged protons and electrons. A single loop contains the energy equivalent to 10 million volcanoes erupting at once. These loops are sometimes the first sign of an impending solar storm. Professor Paul Bellin wants to find out how these loops lead to a solar storm. So he recreates the surface of the sun in his lab.
We have the main ingredients of what goes on in the sun. We set up a magnetic field that is arched. We have a plasma there that can conduct electricity just like the plasma on the sun. And we drive an electric current along the arch just like on the sun.
With all the ingredients of the sun in place, Bellin passes an electric charge through the experiment. Bellin's work shows these arcs are unstable. They twist and stretch in all directions. When they collide, they short circuit, like crossed wires. All their energy is released in a spark, a white-hot flash. The same phenomenon we see on the sun. A solar flare.
It's a little bit like seeing a hurricane develop. You can see the precursors of something that might blow up on the sun. You have currents, magnetic fields, the currents make forces, and if they add up in the right way, you can get very powerful forces that can cause these structures to blow up.
Bellin's lab flares release only a small amount of energy. If the energy packed into a solar flare was unleashed on Earth, the explosion could level whole cities. The The shock waves would be felt on the other side of the Earth. Nearly all life would be wiped out. Far stronger than the world's nuclear arsenal.
The smallest of the flares are more than 1 million nuclear bombs going off. The largest ones are 1 million times 1 million of these bombs going off.
Dr. Carol Shriver studies the power of solar flares.
A large flare is a vast amount of energy. It has no counterpart on Earth.
One solar flare packs enough energy to power America for thousands of years. In 1997, NASA captures this image of the sun's surface the moment after a solar flare explodes. It shows a shock wave, a ripple, racing thousands of miles across the surface. It travels so fast, it could circle the Earth in less than a minute. A solar flare packs a huge punch, but it isn't responsible for Quebec's power failure. It is the first stage of a devastating onslaught. Like the flash from a gun, it's the bullet that follows which causes the damage. Behind nearly all solar flares is a gigantic cloud of radiation, and in its sights, Earth. But its first victims are in outer space. For years, space scientists have known of the threat posed by solar storms. But the sun is unpredictable, and sometimes even NASA can be taken by surprise. May 14th, 1973. America's first space station, Skylab, launches.
Moving up. Skylab has cleared the tower.
Its mission, to prove that humans can live for long periods of time in space, and to expand our view of distant planets and stars. In total, 9 astronauts visit the station. The longest stay is 84 days. But Skylab is plagued with mechanical problems. And in 1974, it is abandoned by its crew and left to await repair. But in 1979, something knocks Skylab out of space. Scientists discover that between 1974 and 79, the sun fires a barrage of solar flares toward Skylab. But it isn't the flares that bring the spacecraft down. It's what follows. Minutes behind each flare is a gigantic wave of radiation. The wave contains huge amounts of electromagnetic energy, X-rays and gamma rays straight from the surface of the sun. The wave travels at the speed of light and smashes into the Earth's upper atmosphere, which heats and expands.
Solar storms, especially solar flares, dump enormous amounts of energy into the upper atmosphere. The upper atmosphere responds by heating up from 500 degrees to 1500 degrees, and that also causes it to expand out by up to 1,000 miles.
The swollen atmosphere envelops Skylab. The space station is suddenly surrounded by air, where once there was nothing but space. Air drag slows the satellite down, and it begins to fall out of orbit. In July 1979, Skylab crashes to Earth. Luckily, much of Skylab burned up on re-entry. Without regular boosts, thousands of satellites could suffer the same fate as Skylab. The multi-billion-dollar International Space Station is at risk.
Even the International Space Station has to worry about solar storms. It typically loses about 75 yards of altitude every day, and during solar storms, it can lose quite a bit more than that.
But the biggest threat from solar storms isn't to our technology. Radiation can kill. NASA's Neil Zapp is all too aware of the dangers faced by astronauts on all space missions.
Our major problem is that we don't have control over the situation. It's not as easy as turning something off or sending someone home or taking them out of an area. It's very difficult for us to get people out of harm's way once they're in orbit.
No one knows when the next solar storm will strike. And they travel so fast, early warning is next to impossible.
We confirm ignition and the thrusters go.
In 1972, NASA has a close call. In April, Apollo 16 lands on the moon. 8 months later, Apollo 17 touches down.
During the space between these two missions, between Apollo 16 and Apollo 17, there was this large event.
A storm breaks on the surface of the sun. 10 billion tons of radiation rains down on the moon. Unlike the Earth, the moon has no atmosphere to protect humans from the effects of radiation. If the astronauts had been here when the storm struck, they would have absorbed a potentially lethal dose of radiation.
It wasn't by planning, it wasn't intelligent planning that provided for putting the event in the dead space. It was actually a little bit of luck of the draw at that time.
But what happens when a massive solar storm is aimed straight at the Earth? We can't simply move out of the way. For all their power, these bursts of radiation are mere ripples spreading into interplanetary space. The solar storm that hit Quebec is a tsunami. March 13th, 1989. Across the Northern Hemisphere, millions witness a dazzling light show called the Aurora Borealis, the Northern Lights. These sparks are a visible sign of a clash hundreds of miles above the Earth's surface, a war between the sun and the Earth's invisible defense shield, the magnetosphere. Nicola Fox knows the shield like her own backyard.
The sun gives us everything that we need to be able to survive here on Earth, but equally it could take that all away in a split second if we didn't have the magnetosphere to protect us.
The magnetosphere completely envelops the entire planet. This invisible shield flows out from the Earth's core. It punches through the South Pole, cocoons the entire Earth, then plunges back down through the North Pole. Without the magnetosphere, all life on Earth would be vulnerable to high-energy solar radiation. These particles can penetrate living tissue and cause severe damage to cells. When the March 13th radiation cloud collides with the shield, most of the charged particles are deflected safely around the Earth and back out into space. But some radiation does leak in at the poles.
And that really churns up the whole magnetosphere, makes it go to very different configurations than it would normally be in. And in order to redress that balance, because nature always has to be balanced, the aurora are powered.
These mysterious displays of colored lights form when solar particles slam into gases in the atmosphere and cause them to glow. The more powerful the storm, the more dramatic the auroras. This high-altitude battle can cause problems for airliners. At the poles, the atmosphere is especially vulnerable to large bursts of radiation. The wave of energy causes havoc in the upper atmosphere, disrupting GPS systems and blacking out radio signals.
During intense storms, passenger aircraft have to divert to lower altitudes in order to regain communication with air traffic control.
On March 9th, 1989, as the radiation from the flare arrives at Earth's upper atmosphere, the battle with the magnetosphere begins. But in Quebec, the power stays on. 4 days later, on March 13th, a second wave of radiation hits the Earth's atmosphere, and the aurora puts on an awesome show. As the northern lights dance in the sky, the lights in Quebec suddenly go out. How does a radiation cloud high in the atmosphere shut down an electricity network on Earth? To find out, NASA develops the OSO-7 satellite. It can aim a battery of UV and X-ray telescopes at the sun. The mission will give scientists their first glimpse of a monster. This white spot might not look impressive, but it's the first image ever captured of the most powerful event in our solar system. It's called a coronal mass ejection, or CME. 10 billion tons of material explodes from the atmosphere of the sun, an enormous eruption. Without Earth's magnetosphere for protection, high-energy particles from the blast could begin to strip away our atmosphere. If a solar flare is the muzzle burst from a gun, then the CME is the bullet. Scientists still don't know exactly why CMEs occur. They're formed from the sun's corona, the atmosphere that surrounds the sun and stretches millions of miles out into space. Temperatures here reach nearly 3 million degrees Fahrenheit, almost 200 times hotter than the surface.
There are magnetic turbulence and magnetic forces lower down in the solar atmosphere that cause literally the outer atmosphere to be blown out into space.
CMEs are an electrified tangle of charged particles and magnetic fields, a superheated bullet of matter from the sun. A CME looks like a solar flare, but it's 100 times more powerful.
Before we knew of CMEs, we thought that the magnetic storms that occurred on Earth were a consequence of this brightening that was seen at the sun, the flare. And as we've learned more about the sun, we've realized that it's the CME that actually causes the magnetic storm.
Roughly half the time a solar flare occurs, a CME follows, but it travels hundreds of times slower.
It is a mass of coronal material that's coming off the sun, and that travels with the solar wind that streams continuously away from the sun at about 1 million miles an hour. So it takes about 93 hours for it to get to Earth.
On March 9th, a solar flare kicks up a wave of radiation from the sun. The wave travels at the speed of light across space. It hits the Earth's atmosphere in just 8 minutes. The coronal mass ejection arrives 4 days later. This is what causes the blackout. Unlike a solar flare, a CME isn't a spray of radiation. It's a barrage.
And all of a sudden, this big addition of 1,000, 100,000 times as much energy is thrown at the Earth.
The CME creates immense electrical currents in the ionosphere. The upper atmosphere practically crackles with energy. The auroras light up the sky as far south as Texas. Rivers of charged particles flow through the atmosphere and induce powerful electrical fields 60 miles below at the Earth's surface. Suddenly, with no warning, a vast current jumps onto the power grid. The surge races through the system, and the network overloads. The lights go out in Quebec.
We're talking about thousands of components in a power grid that are affected simultaneously, and there really is no place to run and hide from the effects.
The Quebec event was rare, but not unique. So how at risk are we? And when will the next solar storm strike?
For solar storms, it's always a question of when the next one will happen. It's not a question of will they suddenly go away.
To gauge the future threat, scientists need to know how often the Earth has been hit in the past. The hottest storms in the solar system have left their mark in one of the coldest places on Earth, the Arctic Circle. Locked within layers of ice is a history of the Earth. The ice keeps a record of solar storms dating back thousands of years. To see how often the storms hit, researchers look for a chemical they leave behind: nitrate.
You can actually core the ice and measure the nitrate abundances, and you find that the spikes in the abundances match up very nicely with some of the more recent intense storms.
By scanning ice cores, scientists travel back to an age when a massive solar storm struck Earth. A huge peak in nitrate reveals a solar storm that makes the Quebec event look like a firecracker.
The most intense abundance change that we see in the ice core data occurred in September 1859. It was so intense that we call it a superstorm event. It knocked out telegraph service in North America and most of Europe, and it was also seen all the way down in Calcutta, India at the time. It was a major worldwide event seen just about everywhere.
The 1859 storm is the most powerful solar eruption to hit Earth in 500 years. It's 3 times stronger than the storm that blacked out Quebec. If it had hit today, it would probably be catastrophic.
When you think of all of the services that rely on electric power, it's rather staggering to imagine the kind of a geographic footprint that one of these storms would have.
After a superstorm, the lights don't come back on the next day.
Most of the transformers that are used by the big power grids are custom order and can take months to replace.
Imagine months without power. Transportation grinds to a halt. The economy nosedives. No running water. No sanitation. Scarce food. Rampant disease. From the space age to the Stone Age, in the blink of an eye.
A solar storm would affect the power grid in an entire continent because these kinds of storms span the entire planet. It's unlikely that in your lifetime or mine, we're going to see one of these superstorm events. After all, the ice core data was 500 years long, and there was only one of these events in 1859. But there are plenty of events that were half as strong or even a third as strong. They are more numerous, and because of that, the long-haul effect of these things could be actually substantially worse than one major storm all at once.
It could be worse. The sun isn't the only star that produces solar storms. Astronomers peer far into the depths of space and watch stars being born and others die. A chance discovery shows just how dangerous space can be. Astrophysicist Eric Feigelson is researching deep space, looking for streams of X-rays. But what he stumbles upon blows his mind.
Instead of finding what we thought we would find, we instead found these rapidly changing X-ray sources associated with young stars. And we were quite puzzled, frankly, for some years.
The stars produce mysterious bursts of monstrous X-rays, solar flares out of this world.
So the strongest flares we've seen are 10,000 times stronger in the X-ray band than the strongest flare ever seen in the sun. When we looked at 1,000 young suns simultaneously in the Orion Nebula, we found that they're typically flaring at this level once or twice a week.
Solar storms like the one that hit Quebec can release as much energy as 1 billion atomic bombs. The star's Feigelson studies produce flares 10,000 times more powerful. The Hubble telescope catches an eruption on a star 450 light-years from Earth. This flare is so huge, if it hit a space colony, it would take out more than their power. It would take out their planet. Scientists call it a superflare. It's not just one star that creates superflares. There are regions of space where nearly all the stars are doing it. 1,500 light-years away is the Orion Nebula. It's a brilliant haze of gas and dust. In X-ray, the dust disappears, leaving only the stars. This X-ray movie was filmed over 13 days. Each tiny flash is a flare thousands of times more powerful than any produced by our sun. These stars are just like the sun, except much younger.
This cluster was formed about 1 million years ago. Now, that may sound like a long time ago, but compared to the sun, which is 4.5 billion years old, these are very, very young stars.
The Orion Nebula is where new stars are born.
They'll all become like our sun. They're just like our sun was when it was a young star.
Space scientist Gibor Basri wants to know why young stars create such huge flares.
If you take a given kind of star, say a star like the sun, there's a direct correlation between how much magnetic activity you see on that star and how fast you spin it. The slower the star spins, the less activity it has on it.
Like the sun, these stars create huge amounts of magnetic energy because their equator spins faster than their poles. The faster a star spins, the bigger the arcs, and the stronger the flares. And young stars spin very fast.
Our sun goes around about once a month. When it was very young, it went around every couple of days or a few days. So that's how much it's slowed down. And that means that the sun is now much less active than it was then.
Feigelson describes a sun we wouldn't recognize.
When the sun was a baby star at 1 million years old, it was 3 times bigger. It was a ruddy orange color. It had huge star spots that whipped around every few days, rotating much faster than it is today. And the magnetic fields, which you wouldn't see with your visible eyes, but you'd see with an X-ray telescope. The magnetic fields would be 10 times the size of the star, crackling and seething with explosions.
Some scientists think if it wasn't for the violent early sun, the Earth and all the planets in the solar system might not be here. 4.6 billion years ago, the solar system is just a cloud of gas and dust racing around the young sun. How it transforms into the solar system we see today is still a mystery.
So the disk is full of dust, and it's sort of the consistency of cigarette smoke. These are really tiny dust particles. We're really pretty puzzled about how you get from dust bunnies to asteroids. It's easy to stick snowballs together, but it's not so easy to stick sandballs together.
Basri thinks the violent young sun helps build all the planets in our solar system. Giant solar storms rip through the disk. The dust particles are forced together. Over time, they fuse and grow. The first embryonic planets are born. Eventually, the solar system is formed. And as the sun ages, it begins to slow down. If it hadn't calmed, life in the solar system might never have developed. Yet when the sun coughs, the Earth still shudders. there's little shelter from the effects of a massive solar storm. The only way to protect our electricity network is to shut it down before the storm strikes. But how do you predict a solar tantrum? Solar storms are a serious threat to our high-tech lives in the 21st century. The race is on to predict when and where the next one will strike. In September 2006, Japan launches the Hinode satellite. Its 3-year mission is to map the sun's complex magnetic fields. The information it sends back could prove key to forecasting solar storms. Hinode orbits 370 miles above Earth. Its camera peers straight into the sun's atmosphere. It returns the clearest pictures ever of the sun's surface. In December 2006, Hinode captures this groundbreaking footage. A magnetic arc snaps, and a huge flare erupts. It blasts into the solar system at more than 1 million miles an hour. Carol Shriver uses data from Hinode to generate the first computer model of a solar storm before it erupts. A detailed map of the sun's complex magnetic fields.
What drives these large solar flares is the magnetic field, and specifically its electrical currents running through the magnetic field. So each one of these strands is essentially an electrical current prefabricated in the interior of the sun, breaking through the surface and becoming visible, and then ready to power a flare.
Where the magnetic fields intertwine the closest, the currents are strongest. Shriver replicates these electrical currents in 3 dimensions.
If we tilt this, we can suddenly see that these electrical currents come up from one place, go up by something like 20,000 kilometers above the solar surface, and come down again.
The model shows a red river of energy equal to 1 billion atom bombs. When the flare erupts, it releases that energy in seconds.
The amount of energy that goes off in this flare is simply astounding. It's the equivalent of 1 million times 1 million atomic bombs going off at the same time.
If Hinode can spot these densely packed lines of magnetism before a flare explodes on the sun, scientists might be able to predict when the next solar storm will strike. Until that technology arrives, space weather forecasters use a method of analyzing the sun's activity developed almost 400 years ago. Sunspots. Sunspots form because the sun's atmosphere is hotter than its surface. The magnetic arcs block the atmosphere, making the sunspots burn cooler than the surrounding surface. 6,300 degrees versus 10,000 degrees. Sunspots come and go in an 11-year cycle of maximums and minimums. Solar minimum has few sunspots and the fewest flares. At solar maximum, 200 sunspots or more, all firing magnetic arcs. A week before the Quebec blackout, astronomers identify a group of sunspots on the eastern edge of the sun's surface. The blackout occurs during a solar maximum. The next maximum is around the corner, in 2012. The sunspot cycle tells us the gun is loaded. It doesn't tell us when or where the bullet will strike. Once the magnetic arcs cross, the trigger is pulled and a flare explodes. It reaches Earth in just 8 minutes, too fast for a warning. But the most damaging part of a solar storm is slower. A coronal mass ejection can take up to 4 days to arrive. If we know when the solar surge will hit, we can save the electricity network by shutting it down. At the Space Weather Prediction Center, scientists keep a watchful eye on the sun. They're looking for any increase in activity, including the buildup of sunspots.
Well, the forecaster today is looking at the data, trying to understand what the sun is doing right now, and then making predictions of the effects on Earth.
Solar satellite technology is young. It's observed the solar maximum only 3 times. Space weather forecasting is where Earth weather forecasting was 50 years ago.
If you were trying to predict a hurricane, if you didn't know anything about the speed of the winds and you didn't know anything about the atmospheric pressure at the eye of the storm and some of those types of things, that would be fairly comparable to where we are now in space weather.
You can see a hurricane coming, not a solar storm. Once it leaves the sun's surface, it's practically invisible. It can hold 10 billion tons of matter, but it's spread over millions of square miles. Just a handful of atoms in every cubic foot.
You couldn't see one of these storms arriving at Earth with the naked eye. They are so dilute that they are actually better than the kinds of vacuums that we can create under laboratory conditions.
Satellite instruments are sensitive enough to detect solar storms, but there's a catch. If one heads straight toward us, it's very difficult to tell how fast it's traveling. It's like the batter in a baseball game. As the ball hurtles toward the hitter, it's impossible to judge its exact speed. 3 strikes, and he's out. If scientists misjudge the speed of a solar storm, 1 strike could take us back to the Dark Ages. To help solve this blind spot, in 2006, NASA launches a 2-stage satellite called Stereo.
Stereo's great. We're going to be able to watch coronal mass ejections from perspectives that we've never been able to see before. And most importantly, it would be the one that allows us to watch the event happen along the Sun-Earth line.
After launch, the satellites separate. They use the moon's gravity to reach their orbits, flanking the Earth. The 2 near-identical satellites orbit the sun, but one of them is slightly ahead of the other. They give the first 3-dimensional stereo view of the sun. Scientists can now forecast very quickly if and when a solar storm is going to hit the planet.
It will improve the timing in particular of the forecasts that we would try to make, to mitigate the consequences of that as it went by the Earth.
NASA hopes that Stereo's information will lengthen early warning times from just a few hours to a couple of days. It could prevent blackouts like Quebec from ever happening again. One day, advanced satellite technology might even predict solar storms before they're born.
It won't be next year. It may be a few years, but it's doable now. We've been moving ahead very rapidly with less and less simplifications, with bigger and bigger resolution, more finesse in the models. And we're getting to a state that we can say that we're actually approximating what really happens on the sun.
Stereo could save our way of life from solar storms. For 2 million years, solar storms did us no harm. Less than 2 centuries ago, we harnessed electricity and got our fingers burned. Nobody knows exactly when the next solar storm will strike. Solar maximum is just 3 years away. And once again, Earth could be in the firing line. Hopefully, this time, the lights will stay on.